Welcome to the massive open online course on Aspen Plus. In this week, we are supposed to perform a case study, two case studies in fact. One is on absorption, the other one is on distillation or stripping. Now, I have chosen a problem in which both these unit operations can work together. Individually, we have learned these two unit operations in other case studies which we have performed earlier. But in this particular case study, we shall take reaction mechanism into these unit operations. In other words, it will be reactive absorption and stripping. Now, the case study that I have chosen here is from this book, CO2 Capture by Reactive Absorption and Stripping, Modeling, Analysis and Design by Claudio Madeddu, Massimiliano Enrico, and Roberto Baratti. Now, this book is available in the internet. You can purchase it or you can borrow it from library if you have it. But this book is needed if you want to solve this problem. Unlike in the previous weeks, I do not have any problem statement drafted. Rather, I will use the problem statements used in this particular book, which has all the necessary information for our case study. So this is the book that I was talking about. It's published by Springer Briefs in Energy. Now, to begin with, you might be aware that carbon dioxide is known to be a greenhouse gas, which is responsible for global warming. And there are various sources of carbon dioxide, but most prominent source is the power plant exhaust, which has flue gas. Now, the flue gas is basically a mixture of carbon dioxide, nitrogen, water vapor, unreacted oxygen, H2S, methane, and other impurities. But for this particular problem, we will not consider any one of them. We'll consider only carbon dioxide, nitrogen, and water vapor. We'll assume only these three components are there in our flue gas. Now, obviously, if the percentage of carbon dioxide is more in flue gas, we cannot release it in the environment because it will create pollution. We need to knock off this CO2. Now, in this book, they have described a procedure to capture CO2 by reactive absorption and stripping using alkyl amines. Okay. You might know that alkyl amines have the capability of absorbing CO2. Whenever CO2 and amine they come in contact with each other, they react and thereby the CO2 gets absorbed in amine. And it is very easy to separate them. If we heat the rich amine, that means the CO2 absorbed in amine, that we call it as a rich amine. If we heat the rich amine, then CO2 gets dissolved very easily and amine gets free of CO2. And that can be reused. So basically we will have an absorption column, which will be a pad column. Flue gas is passed through the bottom, so it will have a combination of CO2, N2 and H2O. And lean amine, that means amine free of CO2, will be poured from the top and they will react with each other. And the rich amine, that means amine plus CO2. Mostly CO2 will be there in compound form. That will come out from the bottom of the absorption column. And a clean gas, that means the gas free of CO2. So it will be mostly nitrogen and maybe some water vapor. And there will be some unabsorbed CO2 will also be there. 100% CO2 removal is never possible. But mostly the amount of CO2 will be very less, so we can safely release into the atmosphere. So we will have the rich amine over here, which we need to heat up to regenerate our amine for reuse. For that, we will take another column, which again will be a packed column. We shall send this rich amine to this column and heat it. Upon heating, CO2 will come out from the top because CO2 gas is lighter, and amine will come out from the bottom as a liquid. This CO2 can be captured through some means. I mean, it will be concentrated and stored somewhere else. That is the purpose, basically, of this system. And this amine becomes lean again because it has dissolved CO2. So it can be again recycled back to the absorption column. So this is the overall process that we will deal with in the case study. Now, in the very beginning, we shall study only the absorption column, and then we will study the stripping column, and at the end we shall combine them along with some other unit operations such as pumps or heat exchanger or valve, etc., and make it a comprehensive case study. Okay, so to begin with, we need the list of components. Now you will see this particular book has been written keeping Aspen Plus users in mind. And all the modeling and analysis tools that have been described in this book refers to Aspen Plus extensively. So in the introductory chapter, they talk about pollution due to carbon dioxide and some brief history, how the carbon dioxide changes the climate and political debate along with it, etc. And they talk about carbon capture and storage technologies. These are not relevant to our study. Our actual study begins in the second chapter where process description is given, how to set the property environment, the simulation environment. Aspen Plus, we will use RAD-FRAC column for absorption and stripping as well. And it will be run in rate-based mode. They will give the information about how the rate-based simulation environment will be designed and so on. And third chapter will talk about the model validation for the absorber, the rate-based correlations, liquid film discretization parameters, all of them will be done. And then some segmental analysis, how the interfacial mass transfer happens, etc. Then chapter 4 deals with model validation of stripper. And finally, a comprehensive absorption plus stripping, both together as a wholesome case study, is presented in the chapter 5. There are other economic evaluations are there that we'll not consider at this moment. So we can directly go to the chapter 2. Yes, so process modeling in Aspen Plus. So here the process description has been given and the simplified flow sheet of CO2 capture by reactive absorption and stripping plant. This will come later. And here, building the model in Aspen Plus, although we know how to do it, but they have given it in a nutshell. We have to add in the components, diffusion in 2 phases, simultaneous mass transfer and energy transfer, equilibrium and reaction kinetics we have to refer and give the parameters in that, vapor liquid equilibria, gas liquid equilibria we have to analyze with non-ideal thermodynamics. All these factors will come in this case study. And then we have to select the property environment. First, components. This particular figure is very familiar to you because every now and then whenever you begin your case study, you have to give the component specification in this manner. What is interesting over here, you can see, other than the complete compounds like carbon dioxide, water, monoethanol, amine, etc., you also have some ions like CO3 minus minus. It's an ion which has been given as a component. Because ionization will take place, there are reactions that will happen in reactive absorption where CO3 minus minus ion or H3O plus ion or HCO3 minus ion, they will be produced. So they have to be inserted in the component list in order to run the simulation properly. And these are the stoichiometry that has to be inserted in the simulation window. And this is the process flow sheet. We'll come to it later. So these are the chemical reactions. Okay. So altogether, we will have a set of 3 ionic equilibrium reaction. That is reaction 1, 2, 3, 2.1, 2.2 and 2.3. These are ionic equilibrium reaction, and there will be 2 kinetic reversible reactions involving CO2. So we will have these 2 kinetic reaction and these 3 ionic equilibrium reactions which we have to insert in the reaction list. And where do we get the parameters from? They are also obtained from various sources like number 6, number 11. These are references. For instance, the kinetic constants for equation 4 and 5, that is these 2 equations involving CO2, they are obtained from these 2 papers, 18 and 32. So paper 18 is here from Applied Energy, published in 2016, and 32 Pinsent, it's relatively old paper, published in 1956 in Transaction of Faraday Society. Okay, so Aspen Radfrac model. Radfrac model is used for this absorption and stripping columns. So you have to use Radfrac column. They can be run in equilibrium stage mode or rate-based mode. We will use it in rate-based mode. And this is the rate-based segment representation of the absorption. This is a well-known figure which you will find in any mass transfer book. And mass transfer occurs with various theories, and you have to choose the correct theory and its rate equations in order to run the simulation properly. This model is based on 2-film theory of Lewis and Whitman. Now, if you want to know further into 2-film theory, you should refer to this particular reference. And film modeling resistance, film modeling, liquid film discretization, everything has been said over here. Now you will come across reaction condition factor, film discretization ratio, number of discretization points in the film. These are the few topics that we will come across while running the simulation. Okay, so this will come later. First, let us go to the Aspen Plus simulation window and start preparing our simulation. This particular simulation involves lot of components and lot of reaction mechanism. So what I have done, I have already included those components and reaction mechanism into the simulation file because there is nothing to teach over there. You already know how to enter the components. You already know how to enter the reaction mechanism. So I just wanted to save some time and done those preliminary work myself without waiting for this lecture. I will obviously show you the final result, but those things have been done. Let me go to the simulation window first. Yeah, so this is the simulation window. Now you have all the components selected, that is monoethanol, amine, water, carbon dioxide, hydrogen sulfide. Now you may ask me why hydrogen sulfide, because hydrogen sulfide may be present in flue gas as an impurity. Obviously not in large quantity, small quantity maybe. So in future, if you want to change your simulation environment, if you want to add in a few impurities, if hydrogen sulfide is present in the flue gas, if you want to add certain number of equations more due to those impurities, then it will be easier for you. You do not have to add the components again and rerun the property method. Okay, so these things I have already added in. If you use it, it's okay. If you do not use it, doesn't matter. It will just stay over here. So this is the comprehensive list of components that you can use for CO2 sequestration. Property method, we will use eNRTL-RK, that is electrolyte NRTL model with Rayleigh-Kwong equation of state and Henry's law. What are the Henry's component? You will find over here. So we have this Henry's component. So these are the selected Henry's component in the problem. And this is the chemistry for MEA. You will find them over here. This one. Okay. We have to add in this stoichiometry. And we have done the estimation, in which I said that estimate all missing parameters. And the result run status, it says calculations were completed normally on this date and this time. Okay. Now we shall go to the simulation window. In the simulation window, we have to add in 3 ionic equilibrium reactions and 2 kinetic reversible reactions. So for that, I have already done that. MEA reactions, you will find this 3 ionic equilibrium reaction and 2 kinetic reactions which are reversible in nature. So this one is forward reaction and this one is backward reaction. For this also it is the forward reaction, this is the backward reaction. And if you want to know the equilibrium constants, I have asked them to compute the equilibrium constant from Gibbs energy for all of them. There are 3 ionic equilibrium reaction. For all 3, I have asked them to calculate from Gibbs free energy. But kinetic equation we cannot do like that. We have to use the power law, which I am using over here with this particular parameters that we have found from the references that I just mentioned. One is from Applied Energy by Enrico and another is from Faraday's Society by Pinsent. It's an old paper. As far as I remember, it is 1956 paper. So from there, we have gathered the data and added. So if you want to know the data, this is the fourth reaction. That is the first kinetic reaction. The second kinetic reaction is this one. These are the data. Third kinetic reaction will be like this. And the fourth kinetic reaction will be this. So these are the four reactions. We shall use it when it is needed. Okay. Now, let us open the flow sheet. Okay, so this is the main flow sheet. We have to add a column first. So radfrac, we use a packed bed column. Let us increase the size a bit. Okay, name it as ABS. This is the flue gas in. This is lean amine in. Lean amine means the amine without any CO2 in it. Fresh amine, in other words. And this will be the gas out, which will be clean gas. That means this gas will not contain any significant amount of CO2. And this is the rich amine. That is amine filled with CO2. We rename them accordingly. We say this is lean. This one is flue. This is rich. And this is clean gas. Okay. Now press next. So it is asking for the specification of the flue gas. So for that, let us go to the chapter 3. Yeah, model validation for the absorber. So there are two selected runs for feed characterization. One is by Tontiwach Uthikul et al. The other one is Razi et al. Now we can choose either of them, but for this case study, let us choose this one. When you do the practice, you can do it with Razi et al. Also. So we'll choose this flue gas. So it is 288.15 Kelvin and pressure is 103.15 kilopascal. So 288.15, it is 288.15 Kelvin and 103.15 kilopascal, and molar flow rate is 0.14 moles per second. 0.14 moles per second, and the composition mole fraction is 19.1% CO2, 10% water, and the rest nitrogen. So we have 0.191, 0.1, and N2 0.709. Total 1. So flue gas done. Then it will ask for lean amine. Yes. Lean amine, it is 292.15 Kelvin. Pressure is same, 103.15. Kilopascal. And flow rate 1.04. So 1.04 moles per second. Okay. And composition, it is 5.5% MEA and 94.5% water. So this is MEA and this is water. So lean amine also has been specified. Now the absorption column. So for absorption column, it will be rate based. Number of stages does not been given. So we can choose any number of stages. We can choose say 15 stages or 30 stages. Okay. And it's an absorber, so we don't have any condenser or reboiler. So condenser none and reboiler none. Streams, flue gas has to be sent from the bottom and lean amine will be poured from the top. So flue gas at 30th stage or on 30th stage, because the stages will be counted from the top. Top stage is 1, then 2, 3, 4. 30th stage is the bottom stage. And lean amine will be poured above the stage 1. Here the clean gas or clean vapor will go out of the stage 1 and rich amine will pass through the stage 30 as a liquid. Pressure, they have not said anything about the pressure at the stage 1. Let us keep the pressure at the stage 1 as 103.15 kilopascal because lean amine is being inserted from the stage 1 at that pressure. So just to keep a parity, we'll keep as 103.15. So 103.15 kilopascal. Okay. So specifications have been given. Now, as it is a rate-based column, so we have to enter the column internals. So go to column internals, add a new. So add a new section. Let us keep only one section in the column. So it begins at stage 1, ends at 30. The sizing will be rate based. It will be a packed column. Packing type. So information has been given. It should be 12.7 millimeter barrel saddles. So we look for barrel saddles. Yeah, this one, it is barrel saddle. And automatically the vendor has been chosen. There are many vendors. Now all those vendors, they have their different dimensions, but we have to choose a dimension which is (12.7), which gives 12.7, because it has been said 12.7 millimeter barrel saddles. So Norton doesn't have it. Gliss, it also doesn't have it. What about generic? None of them has exactly 12.7. So let us choose 13 millimeter. So that is the closest one. And we will keep the default one only. Let us not change it. Packed height, it is 6.55 meter. So we'll write 6.55, and diameter is 0.1 meter. Okay. So it is done. Now we shall come down to rate-based modeling. So here we have to add in a few information. A few minutes back, I was discussing about what they were asking for. They have given some information about how to choose the rate-based correlations. And they said that the mass transfer coefficient has to be calculated from this particular paper, Wanda et al., and heat transfer coefficient from Chilton and Colburn analogy. Now, if you go to this section, first of all, you have to click this rate-based calculation. Once it is done, this is open for you, mass transfer coefficient method. Okay, there are various methods available. Now, they have asked you to choose Onda et al. 9. So, this is the paper, Onda et al. 1968, mass transfer coefficient between gas-liquid phases in packed column. Journal of Chemical Engineering, Japan. Okay, so Onda 68, they have chosen Onda 68 by default. So we will keep it. If you have something of your own, you can use it as user-based, but then you have to supply the model. Now, heat transfer coefficient, they have said you can choose the Chilton and Colburn analogy. So by default it is there as Chilton and Colburn analogy. Interfacial area method, it is again Onda 68. Weighted surface area, Onda 68. And some further information is given. Liquid film discretization parameter. So a reaction condition factor was set to 0.9 in order to give more weight to the bulk condition in the evaluation of film reaction rate due to the first reactions in the liquid film. Okay, what is reaction condition factor and how it is helpful for your simulation setting up? You can go through the work of Zhang et al. And then you can find it. For the time being, let us go to the simulation and look for reaction condition factor and put 0.9 over here. After significant number of simulation, it was found that 5 non-equidistant discretization points in the liquid film were sufficient for correct description of the profiles, and this value is in agreement with work of Kuka et al. So for film discretization, first we will say the liquid phase film should be discretized, and that it will ask for number of discretization point. We'll say 5 because that has been found to be the best. For vapor phase, we'll also consider the film, and then film discretization ratio was fixed at 10. That was found to be a good compromise between discretization points placement and discretization steps for the numerical solution of the system. So we shall look for film discretization ratio and put it as 10. All other things we can just keep it as it is. Okay. So even without that, the simulation is ready for run. So we just run it. Okay, we have got some problem, and I believe the problem lies over here. Yes, so at many places you will see the operating points are lying over here. So many places are getting dried up. So our liquid flow rate or amine flow rate is very, very low. So we will increase the flow rate of amine. So we just open it. Instead of 1.04, let us make it 3.04. So it has been increased almost 3 times, if not exact. Okay, so there is some more problem over here. Let us see what problem we have encountered. We have forgot to add the reactions. Although we have defined reactions, but we forgot to add it. So we will say stage 1 to stage 30, we will have reaction ID of amine reaction. Amine reaction has been defined over here. This is amine reaction. Few minutes back I told you. So that amine reaction will be active from stage 1 to stage 30. And also in the rate-based modeling, we include the mass transfer rate in the report option. Okay. Now run it once again. Okay. Now it has converged. So we are happy that we have a converged solution. And first thing first, we shall first save this simulation, because every time you have a converged solution, make it a habit to save it, because you never know where your solution will go wrong. So if your solution goes wrong and you are not able to come back to the point where you have missed, you can begin your simulation from the saved simulation. You do not have to start from the scratch. Okay. Now, at this moment, let us see the stream results. Now, let us compare the mole fraction. So, we have in the lean gas, we had 94.48% of water. The percentage has increased in the rich gas because a considerable amount of water that was there in flue gas that has come to the amine. And from nearly 10% of flue gas, it has reduced to 2%. CO2, it was 19.1%, reduced to 0.38% in clean gas. So from flue to clean, the CO2 has almost gone. And rich amine is having that amount. Well, you may argue that this is not the figure which can come because 10 to the power minus 9. So amount of CO2 may not be so less in rich amine. Yes, definitely we'll explore it. How? For that you have to see the mass flow rate. Okay, here you see. In the flue gas we had 4.23656 kg per hour of carbon dioxide, and in clean gas it is 0.062 kg per hour. So almost 4.17 kg per hour of CO2 has been taken by the amine. But in rich amine, we have very less amount of CO2. So where is the CO2? Where has it gone? It has gone to HCO3 minus. It has gone to CO3 minus minus. Also, it has gone to MEaCOO minus. So CO2 is mostly in ionic form, not in CO2 compound form. Okay. Now let us check the profile of the liquid temperature. So for that, let us change it to Kelvin. Now we have to compare it with this one. Here they have given the liquid temperature versus distance from the bottom. So this is at the bottom and this is at the top. Definitely at the top the temperature will be lower and at the bottom temperature will be higher. So we should have this kind of graph. So let us see whether we get it. For that, let us copy it and go to Excel file. Now this is stage 1. Now the height of the column is 6.55 meter and we have 30 stages. So each stage is 6.55 by 30 meter of length. So cumulatively, this into this is the length of stage 1. This is the length of stage 1 and 2 together. This is the length of stage 1, 2, 3 all together. Likewise, 6.55 is the length of all 30 stages together. So distance from the bottom will be 6.55 minus this. For everything. So this is the distance from bottom, this is distance from bottom, this is distance from bottom, and so on. So let us insert one scatter. Instead of stage 1, we'll keep this. Okay, now this particular graph is not looking like this one. Why? Because we have got the lean amine flow as 3.04. Now if we run it once again with 2.04, okay, it has converged. Then try with 1.04, the original figure. Okay, this time it has converged. Column hydraulics may not support our okay, to some extent it is running. Anyway, let us go to the profile once again and copy, go to the Excel file, press it, yes. Now we can see the temperature. Well, we have forgotten to change it to Kelvin. Okay, so copy once again, press it over here. Okay. So make it 20, make it 20. Yeah, it looks better. So the trend is the same. Okay, it begins somewhere near 320, ends somewhere near 290. So it's the same trend. What about CO2 vapor composition? So for that, we have to go to the composition, vapor, then mole, and CO2. Copy. Press it here. And instead of this one, yes. So it begins somewhere 0.2 and ends very near to 0.01 or something. So begins somewhere at 0.2 and ends somewhere at 0.1, 0.01 rather. Okay. Now, if you want to see the CO2 interface flow rate, for that we have to go to rate-based modeling, interface profile, mass transfer, unit, moles per second. So copy this one. Press. So instead of this one, write like this, yeah. So this is a bell-shaped curve, yeah. Trend is identical. This is H2O interface flow rate. So this is the H2O file. Instead of this one, yes. So the trend is similar. Okay, now if you change it to, say, from 30 stage to 90, let us see how it changes. Okay, now for that, what we need to do is we need to change the setup from 30 to 90. So number of stages 90. Lean amine is entering on stage 90, and then the reaction is happening up to stage 90, and the column internals, the section is up to 90. Okay, then run it once again. Okay, again we have some results with us. Especially we are interested to know the profile, revised profile rather, for 90 stages. Change it from centigrade to Kelvin. Copy. Place it over here. So instead of 30, we'll say 90 because we have 90 stages. All others will remain same. So we shall add one more plot over here. So for us, this is the x-axis and y-axis is this one. Okay. So you can see the new line, red line, it has gone up. Similar trend is observed over here. For 30, it is somewhere here, but for 90, it is going up. And over here, so after 1 meter, the profile for 30 stage column, it is higher than a 90 stage column. You see over here, after nearly 1 meter, the profile of a 30 stage column is higher than a 90 stage column. If you find difficulty to understand it properly, you can shift it to a chart. Okay, so this one is very much similar to this one. Okay. So this one will also be similar. So that's how we do the rate-based modeling of absorption column for reactive absorption of CO2 in monoethanol amine.
So the purpose of 90 stages column is over. We have done the analysis. Now we shall go back to 30 stage column. Why? Because unnecessarily it is not wise to carry on with a 90 stage column, because it will take a lot of computational effort, and for each and every run there is no need to put on such a computational load on the computer and increase the time of convergence. And that is the reason we are going back to 30 stage column.
We are done with the absorption column. Now we'll shift to the stripping column.